partition representations of S3 using the combinatorial knowledge of what the dimensions of the intertwiner spaces should be. This can be done in a much more general setting. So I'll call this the combinatorial resolution theorem. Suppose you have a partially ordered set. I hope you all know what a partially ordered set is. So it's a set with a binary relation that is transitive and has the property that if x is less than or equal to y and y is less than or equal to x, then x must be equal to y. So the only difference between a partial order and a total order is that in a total order any two elements must be comparable. Either x must be less than or equal to y or y must be less than or equal to x. In a partial order you could have elements which are not comparable. So here we have a partially ordered set. So it's a set P with this binary relation less than or equal to, and we have a family of representations u lambda where lambda is in P. In our example, these will be the permutation representations kx lambda. Let's assume that these are completely reducible representations. And let's assume that we have some way of computing the dimensions of the intertwiner spaces. Let's call them m lambda mu. So these are representations of some group. And further assume that we have m lambda mu is the sum over nu less than or equal to lambda, nu less than or equal to mu, k nu lambda, k nu mu for some family of non-negative integers k nu lambda, with the additional condition that k lambda lambda is 1 for all lambda. So this is the hypothesis, quite a mouthful. And the conclusion is that if you know all this, then there exists a simple representation v lambda for every lambda in P such that u lambda is some mu less than or equal to lambda v mu k mu lambda times. The proof will show that the procedure we used last time always works when you have such numbers. The proof will be essentially by the same procedure. What you do is, so there we had enumerated the elements of the partially ordered set somehow in increasing order. In that case it was a total order, right? For S3 and for S4 also you just had a total order on the partitions, and we wrote down the table of the dimensions of intertwiners in a certain order. So the main point is that we started with something that was minimal. Let's start with something minimal here. Here P should be finite. But I believe this also works under slightly weaker hypothesis. You'll have to see how it works. Start with lambda minimal, then we know that the dimension of end u lambda, well, that's m lambda lambda, and by this equation, which I'll mysteriously call Rsk, we have lambda is minimal, so this set is singleton, the nu which are less than or equal to lambda and the nu which are less than or equal to mu. We have this is k lambda lambda times k lambda lambda, which by this condition is 1. So by now we are familiar with this situation. We'll call this v lambda is simple. Because it's just like we did earlier. And what more can we say? We know that the dimension of Hom G u lambda u mu is, this lambda is minimal, so this set is still singleton and all we get is k lambda mu. This being simple just means that the multiplicity of this simple in this possibly non-simple representation is k lambda mu. V lambda occurs in u mu k lambda mu times, or with multiplicity k lambda. Now we do what we did last time. We remove this many copies of v lambda from each u mu. So you define a representation called u mu 0, which really is defined by this identity u mu 0 direct sum v lambda direct sum k lambda mu is u mu. This you can think of as a definition of u mu 0, and u mu 0 has a nice property that v lambda does not occur in it. Okay, let's calculate dimension Hom u mu 0 u eta 0. You use this equation. So the dimension of the homomorphism u mu to u eta will be an overcount. What the overcount will be the number of homomorphisms from v lambda direct sum k lambda mu to v lambda direct sum k lambda eta. This will just then end up being m mu eta minus k lambda mu k lambda eta. Right. So what is this? If you, is it coming? Okay. So what is this? If you look at this bit, this is summation nu less than or equal to mu, nu less than or equal to eta, k nu mu, k nu eta, but we are leaving out some terms, just one term actually. I can just modify this to say lambda strictly less than. Now look at this family u lambda 0, where lambda is in p, oops, unfortunate choice of notation here. Let us say u mu 0, where mu is in p minus lambda. You leave out that minimal guy, you get a new family of representations, and they still satisfy the hypothesis of the theorem. In effect, we have just reduced the cardinality of P by 1. By induction, you can now get the theorem. So, the theorem follows by induction on the cardinality of P. If P had just one element, okay, that is really just the first step of the proof. Now, the question is, where are we going to get these numbers k nu lambda, k nu mu? We have calculated these numbers for permutation representations when u lambda is k x lambda. These numbers are given by matrices with non-negative integer entries whose row sums are lambda and column sums are mu. So, we want to say that that sum is given by these things. And this is exactly what is provided by the Robinson-Shenstedt-Knuth correspondence, which is a purely combinatorial result. It was published in a paper by Knuth where there is absolutely no reference to the representation theory of symmetric groups. Let me give you the basic definitions concerning the Rsk correspondence. The first definition is that of a semi-standard Young tableau. It is usually abbreviated SSYT. These things have a shape. Lambda, as you can expect, should be a partition, is an array Tij. I goes from 1 to L and j goes from 1 to lambda I. Here I am using the old notation that lambda is lambda 1 dot 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 lambda L, where these things are in decreasing, weakly decreasing order, which is an array which is weakly increasing along rows and strictly increasing along columns. These things are better understood through examples. Let me just draw one for you. What is the shape of this semi-standard Young tableau? I denotes the row number, j denotes the column number. So, this is 1 comma 1, this is 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1 and so on. This has shape, well, there are 6 entries in the first row, there are 5 entries in the second row, 3 entries in each of the third and fourth rows. It has shape 6, 5, 3, 3. The other invariant of a semi-standard Young tableau is its type. This is the sequence alpha 1, alpha 2 dot dot dot, where alpha I is equal to the number of times I occurs in the tableau. What's the type of this? Let's see, 1 occurs 3 times, 2 occurs only once, 3 occurs once, 4 occurs 4 times, 5 occurs 4 times, 6 once, 7 occurs once, 8 occurs 0 times, and 9 occurs once, and then the rest are 0. We'll just terminate this once they all become 0. The type here is not a partition. Let me give you another example. How many semi-standard Young tableaus are there of shape and type 2, 1? So once you fix the shape, it's nice to just draw empty boxes and then fill them out. So I need to put in 2 1s and 1 2. So I can only do this, right? This is shape and type. But suppose I say shape equals 2, 1 and type equals 1, 1, 1, then I get, so I have to put in 1, 1, 1, 2 and 1, 3. Now I have a choice. I can put the 2 either here and the 3 here, or I can do it this way. So there are 2 semi-standard Young tableau of shape 2, 1 and type 1, 1, 1. How many semi-standard Young tableau of shape 1, 1, 1 of any type? Maybe if the shape should be 1, 1, 1, I need to fill in these 3. If I insist that the type be a partition, then what can I do? So then that means the numbers, if some number I occurs, then I minus 1 should have also occurred, should have occurred more times than I. But I can't put any number in more than once because it has to be strictly increasing. So there is only one semi-standard Young tableau whose shape is 1, 1, 1 and type is a partition. If the type was not a partition, I would have done something like 1, 3, 5. There would be infinitely many. But if the type has to be a partition. What about this kind? If I just fix the shape and only say that the type should be a partition, then here for any partition I can find exactly one semi-standard Young tableau of this shape. If the type is just 3, then I could put 1, 1, 1. If the type is 2, 1, then I could put 1, 1, 2, and that's the only choice. And if the type is 1, 1, 1, then I should put 1, 2, 3. So this shape, there are lots of semi-standard Young tableau. This shape, there is only one. These are the 2 extreme shapes, we will see. Let me keep the hypothesis of the theorem. Very suggestively, I should call Kostka numbers. I will denote them by k mu lambda. These are defined to be the number of semi-standard Young tableau of type lambda and shape. As you can guess, these will end up being the numbers in the right hand side of this equation. We just saw in the case of n equals 3, but in general if lambda has only one part which is n, then there exists a unique semi-standard Young tableau of shape lambda and any given type. So what we get is k n lambda equals 1 for all lambda. Oops, we'll say mu. Since I called n itself lambda. On the other hand, k, so this thing with 1 repeated n times is often denoted 1 to the power n. This just means 1 comma 1 comma 1 n times. This is 1 if mu is 1 to the n and 0 otherwise. In this theorem, there is another ingredient. It is this partial order on the set P. Let us see how that comes into the picture. Suppose mu and lambda are both partitions of n. This thing denotes that the thing to the left of it is a partition of the natural number to the right of it. So mu and lambda are partitions of n. It's an easy lemma that if k mu lambda is greater than 0, that means if there exists a semi-standard Young tableau of type lambda and shape mu, then mu 1 plus, you take any sum of the mu's up to some point I, is greater than or equal to lambda 1 plus for I equals 1 2. If you are worried about till where I goes and so on, you just think of extending a partition by zeros, adding zeros at its end. But in any case, this probably ends either when you hit the length of this thing or the length of this thing. You can't always have semi-standard Young tableau of a given type and shape. There is a constraint. This ends up, I think, okay, let us not say a thing about that. This is quite easy to prove. The thing is that each column is strictly increasing. So if you have something in the third row, the things before it must be either, so how many, suppose you have the number r somewhere in your semi-standard Young tableau, then the things that occur above it must be strictly less than r, and they must occur at most once because the column is strictly increasing. So there can be at most r minus 1 boxes above a place where r occurs. So r occurs in one of the first r rows. So r occurs in the first r rows because columns are strictly increasing. Which means that there must be enough space in the first r rows to put in all the occurrences of the numbers 1, 2, 3 up to r, right. But how many entries are there of the form 1, 2, 3 up to r? So, the type keeps track of how many 1s are there, how many 2s are there. So, there are lambda 1 plus lambda 2 plus up to lambda r such numbers from 1 to r. We need enough space for these things. And how much space is there in the first r rows? Mu 1 plus mu 2 up to mu r. Right. So, the amount of space should exceed the amount of stuff you want to put in there. For every r. That's the proof of this lemma. The other thing we need to know for the purposes of satisfying the hypotheses of the combinatorial resolution theorem is that k lambda lambda is equal to 1. For every partition lambda, k lambda lambda is equal to 1. N is somewhat irrelevant here. But what this reasoning here says is that all the numbers up to 1 to r must go in the first r rows. Now, if lambda and mu are equal, then there is just enough room for the numbers 1 to r in the first r rows, which means that no number other than the numbers 1 to r occur in the first r rows. So, in particular, no number other than 1 occurs in the first row. So, all the entries in the first row are 1. Now, no numbers other than 1 and 2 occur in the first two rows, but we already know that all the 1s are in the first row. So, all the 2s must be in the second row. Similarly, all the 3s must be in the third row. So, the only such semi-standard Young tableau are of the form 1 1 1 1. Things like this. So, this has the same shape and type. That is the only one. So, we have got some of the conditions of this theorem. What we need to now do is prove this identity. If we just set k nu lambda to be the number of semi-standard Young tableau of type lambda and shape nu, and we forget about these inequalities, we anyway know that the remaining terms will be 0. Okay. So, if we can prove that m lambda mu is this sum, we would be done without any conditions, inequality conditions, because we anyway know that the terms which do not satisfy this inequality contribute a 0 to this. And that is exactly what the Rsk correspondence will do. So, to start describing the Rsk correspondence, the first thing is to understand Shensted's row insertion algorithm. So, you start with the semi-standard Young tableau you call P, and you insert into it an integer k, and you end up with a new semi-standard Young tableau which is denoted by this symbol. Let me describe this algorithm for you. So, this is called the insertion of k into p. How do you do it? Maybe I should do an example. I will start with this. Here is a semi-standard Young tableau of whatever shape and type, and I want to insert into it the number 4. Okay, usually it is convenient to write it up here, the 4, you will see why. So what you do is you try to push this 4 into the first row. Can I just let it sit here? No, because it would be less than the 6 and we need the rows to be in increasing order. Can I remove the 6 and replace it by a 4? No, again, because there is a 5 here. Can I remove this 5 and replace it by a 4? No, I can't do that. But yes, I can remove this 5 and replace it by a 4. Okay, then this 5 comes out, but I replace it by a 4. So this is the place, and I'll say that the 4 bumps the 5 up, whatever that means. Officially, I'll say let r be the least integer such that P1 r minus 1 is less than or equal to k. If all the entries are greater than k, so if even P11 were greater than k, then I would simply replace the first entry with 4. So I would set r equal to 1. Now there are two possibilities. This r could have been, this r minus 1 could have been the last entry in the row, in which case there would be no P1 rth entry in the semi-standard Young tableau that I started off with. If P1r is not in the tableau, that means the r minus 1 comma r minus 1th entry is the last one in the first row. Just place k at the end of this row. And terminate the algorithm. If instead of 4 I was inserting 554, then I would just place it at the end of the first row. On the other hand, if it is, replace P1r by k and bump up. I'll explain what this bump up means. The old P1r. So bumping up means that I'll take this 5 and try to insert it into the second row. What I'll do is I'll take this 1, 1, 2, 4, 4, 5, 6. And this is the idea is either it rests at the end of this row if it's larger than everything in this row, it's greater than or equal to everything in this row. Otherwise, you must remove something from this row and put it in its place, and you do this in the laziest possible way to keep this thing weakly increasing as you're coming, if you're checking from the right. So the first time you can do it, you do it. And I've replaced this 5 by a 4, and this 5 gets bumped up, which means that I'll try to insert the 5 into the second row. Which means that insert into the next row. This process will end at some point until you add something to the end of a possibly empty row. It could be that you keep bumping up things and maybe this 9 gets bumped up from here to this next row. This is an empty row, you just let it sit there, there would be no contradiction in doing so. So this is the 4 that was inserted here, this is the 5 that got bumped up. Where should I put this 5? I guess I have to put it here. Let me put it here. And it's a 6 that got bumped up. Where can I put this 6? I can put it over here. So it's the 8 that gets bumped up, and I replace this 8 by a 6. I need to insert it into this row. But here it's already greater than or equal to all the entries in this row. I can just bring it to rest here. This sequence of underlined numbers is what is called the insertion path. And this is the insertion of 4 into the original tableau P that I had. So that's Shensted's bumping algorithm. It's just a combinatorial construction. Now it's clear that each row is weakly increasing. We need to make sure that the columns are strictly increasing. Almost everything about this algorithm depends on 2 technical lemmas, and once you master these lemmas, the proofs are a breeze. The first is that the insertion path always moves to the left. It could stay in the same column, or it could move strictly to the left. That is what I mean by moves to the left, means moves weakly to the left. Look at this example. The insertion path starts off in the 5th column, goes down to the 4th column, remains in the 4th column, then comes to rest in the 3rd column. The insertion path is this sequence of coordinates. You can just list them as a sequence of coordinates. So in the first row it was 5, in the second row it was 4, in the third row it was 4, in the fourth row it was 3, and that's it. So this is the insertion path. Just the coordinates of the underlined entries in that picture. Weakly just means it can either go down or it goes strictly to the left. As you go from up to down, of course, that's the sequence in which you are inserting. Formally, this means that if Rs and R plus 1 T are in the insertion path, oops, I shouldn't write P comma K, I should write P backwards arrow K, then T is less than or equal to S, right? Proof is actually nothing much. If Rs is in this insertion path, then there are two possibilities. PR plus 1 S, that is the entry directly below R plus S, is strictly greater than PRS. That is just because P is a semi-standard Young tableau. What is the other possibility? It is that PR plus 1S is just not there in the tableau. We will say does not exist. There is no entry there in the tableau. This is the last thing in that row. In the first case, this PRS cannot get bumped to the right of PR plus 1S, because we already observed that this insertion tableau keeps each row in weakly increasing order. If it did get bumped to the right of this, then that order would be violated. So, it can't get bumped to the right of this. So, it must get bumped either into this place or something to the left of it. So, that would show that T is less than or equal to S. In the other case, well, it would come to rest at the end of the next column, but if PR plus 1S does not exist, then the end of the next column must occur before this. So, it can come to rest either here or to the left of it. In either case, you are covered, and the second lemma is about comparing two bumping paths. Suppose you first insert J into a semi-standard Young tableau, and then you insert K which is greater than or equal to J into that insertion tableau. Then how do you compare the two insertion paths? Suppose P is a semi-standard Young tableau. And J is less than or equal to K. Then you look at this insertion path. This lies strictly to the left of I. Now, you take this insertion tableau and then you insert K into it. The second insertion path will be to the right of the first insertion path. This is you just need to check it row by row. Okay, so if you start with a row, then a number can only bump something that's strictly larger than it up to the next row, right. So, so if you have first inserted J into the first row, then K cannot bump J up. Okay, it must bump something that's strictly larger than J, therefore something that's strictly to the right of J. So, the first step of the insertion path is fine, that it will be to the right of the first step of the insertion path of J into P. Now, also what do you bump up? So, if you take J and use it to bump up something, and then you take K, you bump up something to the right of it in the original tableau, then since you bumped up something to the right of it, it would be greater than or equal to what J bumped up in the first place. Now, both these things are going to be bumped up to the second row, and the same argument can be repeated again. Is that clear? Okay, so it's easier to say these things than to write them down. And from this you can conclude that if you insert an integer into a semi-standard Young tableau, then it is also semi-standard. Here I am assuming that you start off with a semi-standard Young tableau, you insert some number into it, then you also end up with a semi-standard Young tableau. And why? Well, we have already seen that the rows are weakly increasing. What we need to check is that the columns are strictly increasing. Okay. So, we will just check that whenever we bump up something and put a new entry, it is actually larger than what was above it. Okay. So, now suppose at some row stage you are putting in inserting B. B can only bump up something that is strictly larger than it. So, and this goes to a column that is weakly to the left of B. Okay, so I am putting B into some row, and it bumps up something in the first row, but each time after that, when you bump something up, it comes to rest below something strictly smaller than it. So, from the first technical lemma, you see that the Shenstedt insertion algorithm takes semi-standard Young tableau to semi-standard Young tableau. Now, let me give you the RSK, the construction of the RSK correspondence a la Knuth. You start with a matrix with non-negative integer entries. And to that I will associate something I will call WA, it is a generalized permutation. What it is it's two row array of numbers I1, I2, I3 dot 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 J1, J2, J3 dot 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 of some finite length. Now, permutation means these would be the numbers 1 to n and this would be some scrambling of it, but here it is slightly weaker the condition. You just assume that I1 is less than or equal to I2 is less than or equal to I3, and if IR is equal to IR plus 1, then JR is less than or equal to JR plus 1. Yeah, the relation is that K should be greater than or equal to J. That's the main point, right? So, you were asking if there is any relation between J and K, and it is that K should be greater than or equal to J, because that's how we know that K bumps up something larger than J, which we used in the proof, and also that K is inserted to the right of J. Now, what about this? Here these are weakly increasing. If they were strictly increasing, then this would just be 1 to n. Well, if I insist that these numbers are also from 1 to n, then well, it still wouldn't give me a permutation, but permutations are special cases of this. What is this construction? Let me just do it by example. Suppose you start with the matrix 1, 0, 2, 0, 2, 0, 1, 1, 0. then what it is that the number of times I comma j occurs in this is the ijth entry of the matrix. Okay, so if I want to write down the thing corresponding that, I have no choice, but first I have to put 1, 1, that's the 1/1th entry, that's only once. Then this is the 1/2th entry, there's nothing. Then the 1/3th entry, so that happens twice. Then 2, 2, that's also twice. Then 3, 1, and then 3, 2. Okay, so ij occurs aij times. You look at the ijth entry of the matrix and ij occurs aij times. So basically you take a collection of vectors ij and as many as the ijth entry you take, that many times you take ij, and then write them down in lexicographic order. That's what it amounts to. And now you use this to construct a pair of semi-standard Young tableau of the same shape. So you start with P0, Q0 to be both the empty semi-standard Young tableau. That means no box, no entries at all. And then you start, it's an inductive process. If PT and Qt are defined, then you define Pt plus 1 to be Pt with Jt plus 1 inserted. So you take the entries from the second row and you insert them into P, and Qt plus 1 is obtained from Qt by adding a box. You don't disturb Qt itself, but you add a box. Containing it plus 1 in such a way that Pt plus 1 and Qt plus 1 still have the same shape. What this means is that when you did this insertion, you would have created a new box in the shape, and that's where you will put your it plus 1. These things are best understood by example, so let's just continue with this thing. I'll show you the different stages. We can forget about the original matrix. The correspondence now only works with this 2-row array. According to the formula, the construction, you must start with the empty things and then you must insert a 1 into the first one. Okay, so you take the, let me draw a table. I, Pi, Qi. I'll leave out I equals 0. When I is 1, you insert a 1 into the empty tableau, you get 1 here, and then you add a 1 to the empty tableau at that same place. Now I must insert a 3 into the P tableau, and then I must add a 1 at the new box that was created. Oh, let me do it in the next column. So, are you with me? Next stage, what do I insert? yet another 3. The insertions are coming from the second row. Okay, still I just insert it to the right here and I add a 1. Okay, now something more interesting happens. I need to insert a 2 into this guy. Some bumping happens. And the new box created is here. So I must put a 2 here, which is this 2. Then there's another 2. It gets inserted here and the 3 gets bumped up. And there also is a 2. Now I must insert 1. So that will bump this 1 up, which will bump this 2 up. Oh, sorry, no, that will bump this 2 up. 1, 1, 2, the 2 gets bumped up and bumps up this 3. So this is the new box created, and here I put a 3. And finally, it's a 2 I need to add. Let me just do the 7th step over here. So 1, 1, 2, 2, it just adds on to the end of the row. 2, 2, 3, 1, 1, 1, 2, 2, 3, and this 3 has to go into the new box created, which was here. So this is the pair that comes from that matrix. Yeah, it will use the second lemma. It's clear that the first one will be a semi-standard Young tableau because of the because the Shenstedt insertion algorithm yields a semi-standard Young tableau. It's also clear that they have the same shape. So what you have to check is that the second one is a semi-standard Young tableau, and that is an exercise involving the second technical lemma. Sorry, I can't hear you. Oh yes, something wrong here? Oh, this should be a 3. Is it? Okay, so then the rest of it is wrong. No? I did something in my notes. Now let me just correct it. 1, 2, 3, 3, 1, 2, 2, 2, 3. This is 3, 3. This is 2, 3, 3. But I think that side is okay. I have 1, 1, 2, 3, 2, 3, 3. This 2? Oh, because I am inserting this last 2 here. Good. It's a very strange algorithm, but amazingly it always turns out to be the right algorithm. It doesn't just say that there exists a bijection, it's a very concrete bijection. For our purposes, we just care that there exists a bijection over this thing. So suppose A I'll denote it like this. If you construct PQ as I've described above, I'll denote it by P comma Q is the Rsk correspondent of A, and I'll write it like this. Then P and Q are semi-standard Young tableau. You can easily see the types of P and Q because you're saying how many times you're inserting I and J into the tableau. These are inserted into P and these are inserted into Q. These are the column numbers and these are the row numbers. So, the number of times you insert 3 into P is the sum of, so it's the sum of the third column, right? Here it's 3 occurs twice because the third column is only 2 entries. The number of times you insert 1 is the sum of the first column. So, the types are clear. Summation over I Aij. Well, as j goes from 1 to. So, the row sums the type of P is, yeah, this is a column sum, sorry, I is fixed and j is varying. Type of Q is and the nice thing about this algorithm is that it's reversible. If I give you two semi-standard Young tableau of a given type and the same shape, I can construct a generalized permutation by reversing this construction. You can start with this example and see how you should reverse it. You should be able to guess which was the last addition made to this Q and figure out what was the last thing that was bumped up, and then do the reverse bumping and so on, and the whole thing can be reversed. Just think about how each stage happened and see how it can be reversed. So, it ends up being a bijection. This correspondence gives a bijection from m lambda mu to pairs of semi-standard Young tableau, where type of P is mu, type of Q is lambda, and shape of P equals shape of mu. In particular, it gives this equation that we wanted. The corollary of the Rsk correspondence is that by the combinatorial resolution theorem, kx lambda is, or rather there exists simple representation V lambda for every partition lambda of n. Assume that the characteristic of k does not divide the cardinality of n, then there exists a simple representation V lambda of Sn for every partition such that and since kx11111 is the regular representation of Sn, think about why that's the case. You've constructed all the simple representations representations of Sn.